I'm from Boston, and I had considered for a while handing out live lobsters as gifts, but Andy's chocolate is enough, I think. Thank you for giving your time to allow me to discuss a unique fuel savings opportunity. Fuel costs represent from 30 to 50% of an airline's operating costs, as we have already heard. We're all familiar with the use of wingtips and single-engine taxi and other techniques to reduce fuel consumption. I would like to discuss an immediately available opportunity to save as much as 14% per engine in fuel costs. Straight engine core builds to the actual center line of rotation through Axiam's unique computer-aided optimal build assembly processes bring between 2 to 6% in SFC savings. Axiam's partnership with Flight Sciences International brings an additional 3 to 8%, thus giving a total of 14%. Axiam's unique assembly processes methodology differs from the engine manual procedures and tooling, resolves many common engine core build issues, and improves engine performance and delivers cost savings and engine quality and reliability. Next, I would like to show the products available to airlines to capture these benefits and discuss some specific examples. And finally, I'll make some concluding remarks. Axiam provides repeatable, straight-build, software-driven engine core assembly processes about the actual centerline rotation of the engine core. Its proprietary assembly optimization processes consist of software to build each rotor, software to mate rotors to shafts, repeatable assembly procedures, hydraulic rotor build tooling, and fixtures as required. These assembly processes are used together with our proprietary high-accuracy measurement gauges for rotors, shafts, bearings, seals, casing, and blade distribution. Why is this significant? Because it allows for the optimization of blade tip gaps and therefore improved performance by building from the center line of rotation out to the casing, thus yielding performance improvements of 2 to 6% in SFC, 30 to 40% in EGT margin stability once on wing, and 30 to 40% in vibration, and a 10% improvement in wing time. Axiam's assembly processes are installed at the airline's engine shop of choice. Shop personnel are trained, and Axiam provides continuing engineering and service support to ensure peak performance and uptime. Axiam makes the capital investment. The airline pays Axiam only a percentage of the fuel savings. Flight Sciences International has been a leading designer of successful commercial aviation fuel conservation programs since 1992. FSI fuel conservation programs will trim annual fuel costs by 3 to 8%. FSI engineering and process control experts work with airline project teams to develop and implement fuel conservation programs to the unique features of the client's operational environment. They integrate all key areas of an airline's operations that affect fuel use. That's aircraft performance, aircraft weight, flight operations, ground operations, new products, and education. This is accomplished through careful analysis of all aspects of flight and ground operations to determine the best areas and practices for improvements. The company then develops a comprehensive program that will yield immediate reductions in overall fuel usage and costs and increased operational efficiency. Flight Sciences programs enable its client airlines to achieve greater profitability while reducing greenhouse gas emissions. Two of FSI's well-known ideas that have been widely adopted are wingtips and engine shutdown during taxiing. The power of two. Axiom's partnership with Flight Sciences International brings a total of 5% to 14% incremental SFC savings. For Axiom's benefits, the airline needs to convince its engine shop to adopt its repeatable assembly processes. For FSI's benefits, the airline makes the decision on its own. So what does fuel savings look like for a narrow body and a wide body? A narrow body aircraft can save between $500,000 per year and $1.2 million. A wide body aircraft can save between $2.5 million and $6.5 million annually. So what are the benefits of using Axiom in place of the OEM engine core assembly process? For operators, there is improved engine performance, improved engine quality, and reliability, reduced maintenance costs, reduced CO2 emissions, and longer time on wing. For the engine shop, there is improved engine quality and performance while reducing shop costs. An engine shop can now control assembly process build variables and achieve predictability and reliability. As a result, improvements include reduced assembly, trim, and balancing times, the elimination of rebuilds and rebalancing, the elimination of test cell rejects due to vibration, less engine wear, and reduced material costs, improved vibration, EGT margins, SFC consumption, and the elimination of many common engine problems often attributed to balance. Axiom's total assembly time is 1/3 of the time of the engine manual assembly time and consistent for all engines. Engine core builds are always optimal and well within limits on the first attempt. In contrast, rotors built using OEM procedures and tooling typically require about 3 attempts just to fit within the maximum allowable limits. There are often no specified build limits by the OEM for the assembly of engine core modules, leaving the quality of the engine core build up to each individual engine shop. Axiom's assembly processes are installed at the airline's engine shop of choice. Shop personnel are trained, and Axiom provides continuing engine core assembly engineering support to ensure peak performance. Axiom makes the capital investment. The airline pays Axiom only a percentage of the fuel savings. The engine shop makes no payments at all. Axiom's markets are in the aero, industrial, military, space, and power industries. Turbine sizes range from the space shuttle pumps, which rotate at 37,000 RPM, to large power turbines that rotate at 3,000 to 5,000 RPMs. Axiom has about 48 customers and 52 engine models to date for which it's developed assembly processes. So the question is, can others do this? The answer is no, although some may claim they can. The engine manual assembly process is a trial and error method that was developed in the 1950s. It builds rotors to a maximum allowable run-out limit by offsetting the high points of alternate stages. This procedure often results in relatively bowed rotor assemblies, creating performance issues. The mating of rotors to a shaft or another rotor, the building of bearing compartments, and the distribution of blades are largely left up to the individual mechanic. The addition of weights does not straighten a bowed rotor. The extent to which an engine core is bowed determines how quickly performance deterioration and excessive vibration appear. Axiom straight builds about the actual center line of rotation of the engine core gives much better control of the blade tip gaps, thereby improving performance and retarding performance deterioration. Furthermore, high measurement data accuracy, data processing accuracy, and control of build variables are essential elements to achieve build repeatability. What problems appear when the engine core is bowed? Well, core structure bow eventually results in the common engine issues shown on this slide. The engine shop often attributes these issues to balance problems rather than assembly bow because they have built the rotors to run out limits. Balancing does not solve these problems. A straight optimal build about the actual center line of rotation will prevent them. One should note that power by the hour arrangements believed by many airlines to optimize the incentives for engine shops do not optimize performance because these shops build cores to the maximum allowable run-out limits using the OEM manual assembly processes. You might ask, how does Axiom get better results than the OEM assembly process? A different methodology is used to achieve process repeatability. Axiom's methodology is to build all the engine core modules to the actual center line of rotation. Its software calculates the center line of rotation from the parts inspection data. This requires accurate measurement data to a level of at least 1 order of magnitude beyond the level of the variances to which you want to manage. Axiom's measurement accuracy is 20 millionths of an inch, and you want to manage variables to 1 to 2 ten-thousandths of an inch. Most engine core assembly areas in shops have an accuracy of only 5 ten-thousandths of an inch. This is not sufficient accuracy and will yield poor assembly variables control or trial and error. Furthermore, the OEM software, procedures, and tooling also introduce additional assembly variables that make their assembly processes uncontrollable and unrepeatable, resulting in suboptimal performance and deterioration on wing. The unique aspects of Axiom's assembly processes start at the part level at the bottom of this pyramid and move upwards with highly accurate measurement, straight builds, optimal builds for each set of parts, structural alignment of the engine core modules, fully seated rotors, and custom assembly procedures. All these features are integrated in the software and are required to yield repeatable, predictable engine core builds that result in the improved engine performance I cited earlier. Repeatability begins with highly accurate measurement data through Axiom's family of gauges that have a 3D measurement accuracy of 20 millionths of an inch or better and are isolated from the shop's vibration. Part setup and measurement takes 4 to 5 minutes per part. This compares to gauges sold by some OEMs with a 2D accuracy of only 5 ten-thousandths of an inch, which does not meet the order of magnitude criterion. And their part setup and measurement takes more than 30 minutes. Optimal build models are generated in Axiom's integrated software from each set of part measurement data. These predictive build models become the targets for the engine core builds rather than some maximum allowable runout after the build is completed. It's measured after the build is completed. All this data is stored on a hard drive until it is eventually recalled for assembly. The integrated software build models share a common centerline for the rotors, the shafts, bearings, seals, blades, and casings. Axiom's repeatable assembly procedures, software, and tooling are all required so that the actual builds approximate these optimal build models. further rotor bow, or rotor shift as we call it, is created in the test cell and on wing if the parts are not fully seated. The bolting procedure does not adequately seat rotors. Axiom utilizes custom-designed hydraulic build tooling, as shown here, in its assembly processes to ensure fully seated rotor parts to prevent this rotor shift. Axiom's repeatable assembly procedures ensure that the actual builds consistently match the target builds. Engine manual procedures are typically modified 5 to 15% in order to achieve repeatability without changing endpoints. Next, I'd like to briefly present Axiom's assembly optimization process products, or AOPs as we call them, that are used together with one or more Axiom measurement gauge. These products are customized for each engine model. They include application software, tooling, and assembly procedures. Engine core restoration. ECR is Axiom's entry-level product. It is highlighted in light blue. The ECR product is used for the assembly of all rotors, shafts, bearings, and seals in the engine core. Flow path management. A further improvement in engine performance is achieved by adding the casing to the ECR product, as shown in light blue and green. FPM confirms that the concentricity of the casing overlaps the actual center lines of the rotors, thus giving better control of the blade tip gaps. A corrective action on the casing can be taken before assembly, not after it is assembled and then measured. Geometric balance. The distribution of blades about a common center line of rotation is an upgrade to FPM, thus further improving engine SFC, EGT margins, vibration, and wing time. GeoBal, as we call it, is shown in light blue, green, and brown. GeoBal promises to eliminate the need for static balancing and greatly facilitates dynamic balancing. Product development is to be completed in early spring, and then we'll have a beta test at Delta Tech Ops. The Technical Service and Engineering Support Program, or TSCS, is a program to maintain optimal performance and uptime. It provides continuous technical service and engineering support for the shop's engine core assembly processes. This program includes 2 annual preventive maintenance visits by an engineer, during which refresher training, software and procedures upgrades, repairs, calibrations, and test cell data analysis are performed. Assembly processes and equipment are under continuous warranty. Next, I'd like to present some actual case studies. Many assembly and balancing problems are driven by the engine design, the tools available to perform engine core assembly, and the methodology used. Therefore, all shops that assemble a particular engine model by the engine manual should face similar problems. The more recent engine models are designed with tighter tolerances in order to achieve better performance, thus requiring computer-driven assembly to maintain consistent production workflow. The United PW2037 engine. The airline was interested in fuel consumption savings. Also, there was a large spread in the performance variation among engines in the fleet. Vibration issues forced many hours of trim time of the LPT in the test cell in the shop. About 95% of the LPTs required trimming. Engine core assembly times could take days or weeks. After Axiom's ECR installation, only one of the first 40 engines required any trim at all. During the first year, the shop saved $1 million in test cell fuel consumption alone. They saw 2.5% in SFC savings. on their aircraft with this engine. And fleet engine performance variances diminished considerably, and vibration levels were reduced by 2/3, while EGT margins improved 35%. Swissair LF507 engine, this is a Honeywell engine. The problem here was EGT margins were unsatisfactory, and EGT margin variability was too dispersed among fleet engines. EGT margins deteriorated rapidly on wing, prompting premature removals. After Axiam's ECR assembly process was installed, the improvement in EGT margins was to about 20 to 30 degrees centigrade, which represents over 100% improvement prior to Axiam's installation, and remained stable on wing. The average SFC improvement was 6%. TAP Air Portugal on their CFM56 engine models. TAP Engineering and Maintenance wanted to improve EGT margins and SFC to save costs. Wing time was unsatisfactory because the EGT margins deteriorated on some engines, resulting in premature removals. After Axiam's ECR assembly process was installed, EGT margins improved over 40% and remained stable on wing. The average SFC improvement was about 6%, resulting in significant fuel cost savings. Axiam holds the patents for computer-based engine core assembly, not the OEMs. Axiam's practice is to obtain FAA approval for each commercial Aero engine model for which it develops an assembly process. This is a copy of an approval letter for CFM56. FAA approval translates into local authority approval via intercountry treaties. In conclusion, Axiam's assembly processes and FSI's fuel conservation programs enable airlines to immediately reduce costs while increasing revenues, with no incremental investment. Airlines gain a competitive advantage through improved cash flow and reduced engine maintenance costs. Their only payment is a percentage of SFC savings. Engine shops gain a competitive advantage through delivery of a better quality product, reduced assembly times, shop efficiencies, predictability, and reliability. This brings customer loyalty and more business. There's no incremental cost to the engine shop. I'd like to thank you for your attention, and after we break, help yourself to an article that I left at the, a series of articles at the registration desks entitled Fuel Savings More Than Just Winglets, in which Axiam's assembly processes are featured. Thank you.